Okay, so 2.8, we do elementary matrices. So elementary matrices always a square matrix. Means the same size, right? Okay, so elementary matrix. So if we have, so we denote first letter from the E most of the time, right? So we're using E. That means elementary matrix. All right, now we have 0, 1, 1, 0. Okay, we're gonna think undo from the identity matrix. That is correct, right? Normally we have with 1, 0, right? A little bit confusing. 0, 1, correct? Okay, how do we make? Oh, sorry about that. 1, 0. 1, 0. All right. From identity matrix, normally we have a matrix that we make identity matrix, right? Like a RREF. But in this case, elementary matrix, we're gonna think backward from the identity matrix. How do we make this one? So we change the rows, right? So then we can make that, right? Yeah. Okay, how about other one? We have 1, -3, 0, 1. Now, so think from identity matrix 2 by 2, so 1, 0, 0, 1. So how do you make this one?
-3R1.
3 row 1 -3, yeah, so -3 row 1 plus, not plus, correct? Plus 3 row 3, right? Make sense? Oh no, we don't have row 3, right? What I'm doing right now. Yeah. Is it correct? Yes. Oh, negative. Yeah, I forgot negative. Yes. Okay. So you guys okay with this? So we do backwards. In general, we make from matrix, make identity or REF, right? But now we're gonna think backward. From identity matrix, how do we make elementary matrix, right? Okay. Let me write down the definition. Definition 2.8.1 elementary matrices and row operation. Okay, always square matrix for elementary matrix. So E equal to M by N. And we denote elementary matrix, right? Then we are thinking about from the identity matrix, what kind of row operate we did that, right? To get this one, right? So here, if it is the result of applying only one row operation to the n by n identity matrix. Yeah, let me denote it this way. Row operation, like elementary row operation, we have a interchange like what we did earlier, and we can multiply, and we can multiply scalar by scalar and add, right, to another row like that, right? So we did that before, and then we keep doing this for row echelon form, reduce the row echelon form, right? Okay, but then in that case, we apply only one. Only one means that nothing else. Look, just interchange the rows, right? Just only one. Here, multiply by scalar, add another row, replace. This is a replace, right? Only one. Okay. All right, let us do this one. 3 by 3. So we have, let's denote just is the one, because there's too many elementary matrix. We have 1, 0, negative 4, 0, 1, 0, 0, 0, 1. Okay, what kind of row operation we apply here? So think from the identity matrix, since 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we think backwards, right? Thank you, drawing message. So we multiply, oops. We multiply negative 4, add row 3, right? Then we get replace row 3, right? Can you see that? So there will be negative row 1 plus row 3, replace row 3, right? Okay, how about this? We have 0, 1, 0, 1, 0, 0, 0, 0, 1. So we're gonna think from identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, right? All right. How do we make this from identity matrix? Interchange? Thank you, during my chat, during my chat, during message. So this will be row 1 and row 2, right? Exchange, right? Interchange, switched, right? Okay. How about we have 1 0 0 0 1 0 0 0 5. Okay, we're gonna think from identity matrix 1 0 0 0 1 0 0 0 1 backward. How do you do? Thank you, drawing message. So everyone can see that it's just a scalar multiplied by scalar, right? So that is 5 row 3 to make a row 3, right? Okay, now we have theorem. Two point 8.1 multiplication by an elementary matrix and row operation. So let me just skip the title. To perform any of the 3 row operations. So we had the first one, interchange the rows. Second one, multiply by scalar like this, right? And third one, like multiply by scalar and then add another row, like replace this one, right? Number 1, number 2, number 3 in row operation, right? Okay, they talk about 3 row operation. On matrix A, a surface to take the product EA, so elementary matrix and the matrix A, we multiply them where E is elementary matrix obtained by using the desired row operation. On the identity matrix. Okay, means that the elementary matrix E is created by performing by the same operation on the identity matrix, all right? Okay, let us do this example. Okay, from the interchange one. So we had interchange one, this one, right? Copy? Yeah. We had. All right, now we have A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let's check that. Product of EA means that we have E elementary matrix here. Copy? And A. Okay, let's check the size. So this is 3 by 3, right? And we said the elementary matrix always a square matrix, right? Okay, now A has 3 by 4. So they have a match. So this will be 3 by 4, right? Okay, so let us do this. So first one with the first column, so 5, and second row with the first column, only 1, right? And third row with the first column, only 9. Okay, first row with the second column, only 6. Second row with the second column, only 2. Second column with the, sorry, third column with the second column, third row with the second column, only 10, right? Okay. First row with the third column, only 7. Second row with the third column, only 3. Focus. Third row with the third column, only 11. Okay, the last one. First row with the last column, which is 8. And second row with the last one, only 4. Third row with the last one, which is 12, right? Oh, thank you. Your message. Good. Okay. The person checked that is correct. Good job. All right. Let's take a look. Let's compare with this one. From A, what can we conclude? Yeah, this matrix from this one. What can you see? Thank you, during message. So can you see that? Compare with the original matrix A, and then we have product of elementary matrix and the A, right? then we can see that the rows are switched, right? Can you see that? But then look, we had the elementary matrix. We knew that their rows are switched, their rows are exchanged, right? So by the theorem, in matrix product, we have same row operation, all right? Which is, so row 1 and row 2 exchange as well in product of elementary matrix and A, since they exchange in the elementary matrix, all right? Okay. Let us do one more. Why we are doing this one, elementary? So each elementary matrix is invertible. Note each elementary matrix is invertible. Okay. Let me write down a little bit more. The inverse of E is the elementary matrix of the same type that transform E back into I. Okay. So we had this already. Negative 4R1. This one. Okay. So we have this one. So we had this one, right? And then we knew that if we using this row operation, which is replace operation, right? Then we could get the elementary matrix from identity, right? Okay, now, how do you find the inverse of the elementary matrix? Yeah, so we can do it. Since they label, first one, we can just say that. All right, so inverse. They say that transform E back into I. All right. Then we are going to think about again. We had earlier from identity to think about how we make elementary matrix, right? But then we have elementary matrix. We're gonna change it to identity. All right. Okay. Make a circle. Huh? Okay. How do you make this one to make 0 there? Then everything is identity matrix, right? This one. Think 22 identity. So we're gonna think about how do we make 0 there? How? So we will get, thank you, direct message, if 4 row 1 plus row 3 to make row 3, right? Yes. Then look, we are going to use 4 here. This one. So look, 1 0 0 0 1 0 4 0 1. Okay. All right. Now, how do we check? We're gonna check that elementary matrix and inverse of elementary matrix. Then we get the identity, right? Okay. Embedded tutor. Can you please check that?
Yeah.
Okay, we have, let me see. We have,
if we multiply those two matrices, it will go back to identity. Yeah.
okay, you got that already? All right. Wow. 0 0 1 1 0 0 0 1 0 4 0 1. Okay, there will be identity, which is 1 0 0 0 1 0 0 0 1. So you guys okay? Yes? All right. Let's move on. So I need a little bit more time again for today. All right, so we do 2.10 LU. So title is like LU, but then actually there's LU factorization or decomposition. Composition, right? Okay, we know what factorization means because we have 6, then 2 times 3, that is factorization, right? Okay, so if we have matrix, we can make that form, LU form, right? So that's why we have a factorization, LU factorization, LU decomposition, all right? So we're gonna make a product. Then what is the L, what is the U? L is upper, not L. L is lower, so we're using the first letter, right? So let me write down lower, triangular matrix, And what is a lower triangular matrix? So it's a square matrix. Whose all elements entries, right, above the main diagonal are zeros. Okay, for instance, example like this: 2, 5, -2. So this is a 3 by 3. So 1, -1, -1. And look, lower. So we have a diagonal here, then above there, all the 0, right? So 0, 0, 0. So we can fit it out, 3 zeros there. Okay, so if we draw a triangle here, look. Yeah, we can see that triangle there, right? All the real numbers. We might think about that. So it's a lower triangular matrix. It's like this. How about U? U is upper. So it's the opposite, right? Upper triangular matrix. So everything is the same, but instead of above, we're gonna say below. Below the main diagonal are zeros. So looks like this, right? So we have 3 by 3 again. So 2, -1, 3, 5, 2, 2. So below, so 0, 0, 0, right? So we can draw a triangle on the upper. So looks like that. Yeah. So lower triangular matrix, upper triangular matrix. Okay, now. Then how do we make a product? So in this case, we have to make a unit. Lower triangular matrix must be unit. L must be unit, lower triangular matrix. So unit means the order diagonal is 1. Okay, so for instance, we have L. Okay, let me make a 4 by 4 in this case. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So diagonally. Yeah. Oh, no. What I'm doing. I'm so sorry. Don't copy, please. What I'm doing. Why I'm doing this one. I was focused on only diagonal. Okay, so we can get to any number, right? So any number. So stars any number. Yeah. Okay. All right, let us do that. How to do it? So we're gonna use a multiplier method in that case. All right, so 2 by 2, let us do this. And then we do 3 by 3. Oh, one more note. We cannot use interchange row operation. And use interchange row operation. Okay, so we have only multiply by scalar or replace multiply by scalar and add another row, right? Okay, so we have A equal to 11, 1, -4, -4. Okay, I want to make a for U first. So U, like we are using like reduce to the row echelon form. So but we don't do that, right? Because we have to follow that the what is called upper triangular matrix, right? So but then similar concept, okay, means that we want to make a 0 there, right? Yeah. For you, okay, so for you, we want to make an upper triangular matrix. Okay. So how do we do? Okay, we make, thank you very much in direct message. We make -1/11 R1 and then add R2 to make R2, right? So we will have 11 and -4. So we get 0. Then we get -40/11. Is it true? Okay, so look. This is already upper, right? Because 2 by 2, so we done, right? But then look, how do we make the lower triangular matrix, right? So let me write down for you for lower triangular matrices. Okay, this is the quick way, right? We make a lot of steps. I mean, we can skip a lot of steps because we can just using this one with the opposite side. Okay, so we are using this one. opposite sign. Okay, so you look, I'm sorry, oh my gosh. L. So L, we have to have unit, right? Unit, unit lower triangular. So diagonal is 1. So I'm gonna make a diagonal is 1. Okay. All right. So then here is 0, right? We set it up this way, right? So diagonal and then 0. That's the by definition of lower triangular matrix, right? And then this one, how do you fit it out? So we are using same number here, but then opposite sign. So that will be 1/11. Okay, so there will be A equal to maybe TA can check that LU, which is L 11 negative 4 0 negative 40 11, and we have 1 0 1/11 1. Okay, so I don't have to show this one. You guys can calculate, right? Yeah. So can you please check the answer whether we get this one A? Let me write down here. Yeah. It's okay? Correct? Okay, let's move on. Let us do 3 by 3. Find LU factorization for A equal to 1, 2, negative 2, 2, 3, 3, 3, 1, negative 2. Okay. U first now. So we want to find the U. Okay, so upper. So we are making 0 here, 0 there, 0 there, right? Yeah. I have a heavy RREF, but it's not. Okay. We want to make a 0 here. How? So let us make a R1. So 1, 2, 3. Negative 2 row 1 plus row 2 to make row 2. Yeah. Okay, so I got 0, negative 1, negative 5. Okay, now we want to make a 0 here. Still using row 1. So positive in this case. So we have a 2 row 1 plus row 3 to make row 3. So we get 0, 7, 4. Okay, done, right? So we are making 0 there, then we are done. Equivalent. So that's 7 root 2 plus root 3. Replace root 3, right? Okay, so there will be 0, 0, negative 31. Okay, so there will be u. Okay. Now for L, so we are using all the numbers here, right? Scalar, but then opposite sign. So look. So we have a 3 by 3 unit 1, 1, 1, and lower triangular, so 0, 0, 0. Yeah. Okay. Okay, let's fit it out. So we start to negative 2 is the positive 2 here, and positive 2. So negative 2, 7, negative 7. Yeah. Okay. Very good. So 2, 2, negative 7. Now we have A equal to LU. So A equal to that. Copy. Equal to L. Let me just make that. L. Make it smaller. Oh, come on. Come on. I can make it smaller, so I can make a new there too. Come on. Listen. Equal to U. Okay, can you please check that? This answer is correct? Yeah. Okay, let us do one more. Then we are done. All right, so did I make a mistake? Okay, change it back to, okay, I made a mistake. Okay, hold on. One is positive, one is negative. Correct. Yes. Yes, I remember that. This one, right? So it's a positive, and this one should be negative, right? Yes?
Yes, yes.
Okay, thank you very much. Thank you so much. Yeah. Good job. All right. So find LU factorization. of 693 negative 2 negative 1 7 0 1 5. Okay, for you, right? So we are making 0 0 0. So we want to make a 0 here. Third row for you. Hold on 1 second. Third row for you. Let me see. Third row for you. That is correct, isn't it? Yes. Yeah. I did not. Oh, I
Yeah.
copied wrong one. Sorry,
Yeah.
I copied wrong one. Oh, good thing you checked that, right? Thank you very much. I copied wrong one. It should not be this one. Thank you very much. Ooh, this is the one. Yeah, I need to copy. Thank you. That is the one, right? Okay, now good. All right, so okay, now we could make a -3 here, right? -3. Yeah. To add this one, row 2. But then sometimes number is not nice. Then how do we do, right? So maybe from this number, let's try. Yeah. We could do that. We could do this one, but sometimes number is not nice. Okay, let us do that. How do we find, right? So think, because when I help a student during homework. So we want to make some number 6x, add 9 to make 0, right? Then what's the x? -9/6, which is -3/2, right? Okay, there will be -3/2 row 1 plus row 2. Replace row 2, right? So we have a 6 -2 0. Okay, we know that the first one is 0 because we made 1 from here, right? Okay. Second one, -3/2 R1 row 1 plus row 2, right? Then there is -4. I made a mistake. No, that's not. Yeah. So it's a positive. It's a 2, right? Okay, now. How about third one? So we get 2. So negative, wait a minute. Oh, this is just 1, right? Struggle again. Okay, now. How about we want to make it 0. Very good, thank you. So we make 1/2 row 1, add 3, then replace that, right? So we get 0, 8, 5. All right. Okay, almost done. Good, thank you. We want to make a 0. Fix -2, 0, 0 to 1. All right, so -4 row 1 plus row 3, replace row 3, right? Okay, so that will be 0, 0, 1. So we done, this is U. Okay, now for L, using opposite sign from the scalars. Okay, so we have, okay, hold on 1 second. Let me write down first. L. So 3 by 3. So 1, 1, 1, and 0, 0, 0, right? And -3/2, which is +3/2. And I don't make a mistake, it's a -1/2, negative. And I don't make a mistake, it's -4, it's +4. Now, can you please check that? Check it out. A, L, U. A was copy. And make it smaller. Okay, equal to L. Copy. And U. Copy. Come on. Okay, what this one come from? 3. 3 there. All right. Okay. Thank you very much for checking the answer. So we done. Thank you very much for coming today. So you have a nice day. I mean, sorry, nice evening.
Thank you. Have a good night.
Thank you very much.
Thanks,
And you have